Also, if anyone has a mic, if you tap and hold the space bar, it will like temporarily unmute, and then when I let go of the space bar, it will mute myself back.
Okay, good to know. Thanks, Milo. Okay, so we are now recording. Let me just verify that it agrees that it's recording. Okay, good. Yeah, it looks like it is recording. Okay, so here's my plan for how we're going to do this every day. So it takes the Zoom people about an hour after the class is over before I have access to the recorded video. So about 2 hours after the class is over, I will post the recorded video, and I will also post a quiz, and it'll be a really simple quiz just to verify that you actually watched the video. I mean, it'll be questions like, for instance, what color shirt am I wearing, or something else where if you attended the class or if you watched the video, it will be a very, very easy quiz. Okay, so that's basically my way of taking roll. So if you don't do that, then I can't give you credit for participating. So that's how I take roll. So make sure that you take that online quiz, and I'll keep it really simple. Okay, next, you can see that our next homework assignment is out of the book is 20A. It's very similar to the homework problems we've done before. You just have to read the book, do some of the problems. Now, when you submit the answers, I'll let you do it 2 ways. One is you can go, there's a text box in Canvas where you can go and just type in the answers. Or if you prefer to do it on paper and take a photograph and upload files, that works too. And then, so the next class will be March 30. So my plan is to have a class every Monday, Wednesday, Friday, starting at 1 o'clock. I would ask you to reserve an hour and a half, but I will try not to take the full hour and a half most days. I'll try to keep it down to an hour most days. And then you can see after that class, there's going to be another quiz and record video. So that's basically how it's going to work. Okay, so looking over here, that's midnight Saturday. Sunday is the 29th. Oh, ouch. You guys aren't going to count that as a wig point, are you? Oh, you are? Oh, you guys are so mean to me.
Wear the wig,
Jaren.
Hendricks.
Jaren's my man. Jaren says no. But it looks like, Jaren, you're getting outvoted. Okay, so there's one wig point. Hopefully I won't get 2 more. Okay, so are there any questions about how the class is going to run? So I'm looking over here. Oh, okay. All right, I'm just going to move along then. Okay, so normally this would be the time where we go over the homework and see if you have any questions on the homework. But right now there really wasn't any homework because our last time was a class test. So let's just go ahead and get into the new material here. Oh, what will the extra credit be? We'll talk about that later. Okay. All right, so chapter 20, static electricity. The picture that you see in the book here is a lightning bolt, which actually is not really static electricity. That's dynamic electricity. You guys understand the difference between static and static and dynamic. So static is when things are not moving. Dynamic is when they are. So people do think about lightning when they think about static electricity. Lightning happens because static electricity has built up in the clouds. So you've got so strong of a charge built up in the clouds, they just can't hold it anymore. And so then the lightning bolt shoots. So for a brief instant, it's actually not static anymore. It's actually dynamic for a brief instant, but the thing that leads up to it is static. So we're going to be talking about static electricity in chapter 20, and then later we will get into dynamic electricity. Okay. So when people think of static electricity, this is basically what you think of. Anybody know what that silver ball is called? Let's see if anybody can type it in. There's a name for that silver ball. And I have one of them, not here at home, but I have it at school. The one I have at school is not quite as powerful. Van de Graaff generator. Yay, Milo, way to go. Round, shiny, sappy blade. Okay, I'll go along with that. Perm machine. Okay, I like that a lot. Okay. So the Van de Graaff generator that I have at school is not quite as powerful as that. It won't make your hair stand up quite as dramatically, but it will a little bit. Okay, so that's basically static electricity. So you guys know static electricity. So if you walk across the carpet, especially if you are wearing rubber-soled shoes, it does work with leather too, but it works best if you're wearing rubber-soled shoes, so like running shoes or something. If you shuffle your feet as you're walking across the carpet, when you reach out and touch the doorknob or some metal object, you get a zap. And it's exactly like lightning. It's because what has happened is so much static electricity has built up that as soon as you give it a path where it can escape, it will spark across there. So that's static electricity. Let's see. Every once in a while, I have to look over here to see if anybody has posted questions. I don't see any now. All right, so these are screenshots from the book. And what you see right here is, so what they've done is they've taken a ruler. I should have got a ruler. I don't have a ruler. Okay, we'll pretend this is a ruler. Okay, so they've taken a ruler and they've either rubbed it in their hair or rubbed it on their shirt or something. And so it's built up a lot of static electricity. So when they hold the ruler close to a bunch of these little paper shavings, they stick to the ruler. Okay, and so the deal there is because the ruler has a bunch of charge built up on it, and so then they jump up to it, and we're going to talk a little bit more detail about how that works later. But that's an example of static electricity. Another good example that you see here, if it'll let you. Okay, so this is a good example, and this is the example that I like. Take some tape, and so right now the tape is on here. So what I'm going to do is I'm going to pull off a big long piece of tape, and I let it go. And you see that? You see how the tape is sticking to my hand? So I get it down there, but no, it's still, the tape wants to stick to my hand. Okay, and what's happening there is that you've got two dissimilar materials. So the tape here on the one side, it's sticky. Okay. On the other side, it's not sticky. So you've got different materials on there. So if I take one piece of tape, another piece of tape. Okay, so I'm going to stick the one piece of tape to the back of the other. Okay, so these guys are now in contact with each other. And when I rip them apart, one of them wants to retain electrons more than the other one does. In your chemistry class, you've talked about something called electronegativity, right? So give me a yay or nay. Have you talked about it?
Yes, we have.
Yes. Okay. All right, good. Okay, so when we have these two dissimilar materials here, okay, and I rip them apart, one of them will tend to hold on to the electrons more than the other one will. And so they build up charge. And so now, see, they don't like each other anymore, but if I hold them this way, then they do, okay, then if I hold them, okay, then they do like each other this way, okay? So you guys have all learned in junior high school, you know, like charges repel, opposite charges attract, right? Okay, so that's what's happening here. Remember that, like charges repel, opposite charges attract. Now in junior high school, you probably left it at that, but this is senior high school. So what we're gonna have to do is we're gonna have to do some calculations. We're gonna have to calculate how strongly do they attract or how strongly do they repel. That's gonna be the majority of our homework tonight. Okay, but before we get into that, okay, let's see what's happening here. So here's another example. So what you see right here, I hope you guys can all see my pointer. Yeah, it looks like you can. Okay, so we've got a hard rubber cylinder or rod, and we got some wool. So when they're rubbing them together, then again, they have different electronegativities. So one of them wants to retain the electrons more than the other one does. So one of them gets charged up in a way that we call positive charge. The other one gets what we call a negative charge. And okay, so that's basically how electrostatics works. I see Jaren is saying more of one attracts another greater when there's less of it. Okay, yeah. Yeah, let's just move on. Okay. So we now know about charge. Now, here's another important thing. Conductors and insulators, I'm pretty sure that you guys understand this, but it's worth hitting for sure. So pretty much all materials can be divided into two different groups. Do they conduct electricity or do they not conduct electricity? So conductors and insulators, right? It turns out that nothing is really a perfect conductor or a perfect insulator. Everything is somewhere in between on the spectrum. So can somebody type in something that you think is a good conductor? Let's see what you guys can throw out as examples.
A metal rod.
Okay, so I see gold. A lot of people are saying gold. Some people are saying metal, copper. Okay, so anything that's a metal will be a conductor. Now, different metals conduct differently than others. And most of you there said gold. But, you know, interestingly enough, it turns out that gold is not really all that conductive. I mean, it is metal, so it is conductive. But the other metals are way better. Copper is a much better conductor than gold is. Silver, Theo is saying silver. Yeah, it turns out that silver is actually probably the best conductor out of all the different metals. But because silver is so expensive, they don't use it in wires. They use copper in wires. Okay, so salt water. Okay, so Hunter is suggesting that salt water is a good conductor. And that's absolutely true. Oh, speaking of which, let me come in here, just throw a couple of things on here. So, oops. Okay, so metals. Metals definitely go over here on the conductor side. They are not perfect conductors, but they are definitely good. Okay, so, oops, try that again. Okay, so salt water. Let's try that. Whoops, come on. Okay, so let's try salt water. Let's spell it correctly. Okay. So what do you guys think? Salt water, should that go like in the middle here, or should be over on this side or over there? What do you guys think about salt water? How good of a conductor do you think it should be?
To the left of metal.
To the left of metal, yeah. So it's definitely not as good a conductor as metal is, but it turns out it is a pretty good conductor. So if you guys are ever working on electrical things in your homes, make sure you're not standing in a puddle of water at the time, because it is a good conductor, and it doesn't have to be salt water either. Just tap water, just regular old tap water. In fact, tell you what, let's do it over here. Okay, so here's tap water. And let's turn these guys on their sides like that. Okay, so tap water is a pretty good conductor. The more salt it has in it, the better conductor it's going to be. How salty? Well, the saltier, the better conductor it's going to be. Okay, how about insulators? I want you guys to throw out a couple of things that you think are insulators, and let's see where they fall on here.
Rubber.
So rubber, glass. Okay, so let's put them here. So rubber, and I'll turn it sideways. Yeah, I would put rubber probably right about there. There are different types of rubbers, and so the conductivity of those will vary. But in general, rubber is going to go over there. Now, wood is a really interesting one. And so Ellie said wood. So let's see about wood here. Okay, so here's wood. Okay, wood is really interesting because it depends on what kind of wood, and especially it depends on how fresh it is. If it is wood that you just barely cut from a tree, just that same day, so it still has lots of water content in it, that wood could be over here. It would be a pretty good conductor. As the wood dries out, it's going to become less and less and less conductive. And so if it's thoroughly dried, in fact, especially if it's been kiln baked, you know, when you go to Home Depot to buy lumber, that's all been baked in a kiln. So in that case, it's going to be over on the insulator side of things. Ceramics are definitely good insulators. Big old rock, okay, all right, that would be a pretty good insulator. Air is a pretty good insulator. Okay, now thanks for that. Hold off on that now. So if on the one side here, so over here, this is the things that are really good conductors, and the things over here, they're really good insulators. What would you recommend that we should call something in the middle? Like, let's say I've got wood here it's not completely dried yet. So it's not really a conductor. It's not really an insulator. If only there was a word we could use for a category of things that are not exactly conductors and they're not exactly insulators. They're somewhere in between. If only there was a word for that.
Semiconductor?
Semiconductor, thank you very much. Okay, so here's what I want you guys to do is you take notes. So in your notebooks, and I know you're all taking notes, right? In your notebooks, I want you to draw what you see on the screen right now. I want you to draw an arrow with, you know, a two-sided arrow. On the left side, we have perfect insulator. On the right side, we have perfect conductor. And in the middle there, I want you to write the word semiconductor. I'll wait while you do that. Okay, has everybody done that? Now, here's what I want you to do. I want you to cross out what you just wrote, okay? Put a big old X through the word semiconductor. Now, semiconductor is a logical term that would make sense, that something that's somewhere in between, you know, semiconductor is a logical thing to call it, but don't do that, because the word semiconductor has already been claimed. Semiconductor has a very different meaning. And I'll tell you in just a few minutes what that meaning is.
Well, I know silicon's a semiconductor, and because of the properties of a semiconductor, that's why it's used in computer chips.
Okay, that's a true statement. Okay, so I want everybody to write down semiconductor. I want you to cross out the word semiconductor, and I want you to replace it with partial conductor. Okay, so if something is somewhere in between being a perfect insulator and a perfect conductor, let's not call it a semiconductor. Let's call it a partial conductor. Okay, so if a semiconductor is not that, then the question becomes, well, then what is a semiconductor? Okay, and so the answer to that is a semiconductor is something that can be a good conductor when you want it to be, but with relatively simple modifications, you can make it be a good insulator. So depending on how you treat it, it can either be a really good insulator or it can be a really good conductor. And it's relatively easy to switch it between those two states, okay? Hang on to that. In just a minute, we're gonna come back and we're gonna talk about how we could use that property to great advantage. In fact, it's semiconductors that are allowing us to talk to each other right now. If it weren't for semiconductors, the world as we know it would not exist. So we're going to come back to how semiconductors work. But let's move on, hit a couple things that I want to cover first. Let me just check. Okay, all right, so no new comments there. All right. Okay, so remember when we were talking about the way that various objects can cool down? If you've got a hot object can cool down, remember that we talked about it can cool via conduction, or it can cool via convection or through radiation. So conduction meant that you take the hot object and the cold object and you put them in contact with each other, in physical contact. So then the heat, the thermal energy can flow from the hot one to the cold one. Hang on a second here. Somebody's got their microphone on. Somebody's got their microphone on, and I'm going to mute you all so that we don't hear when you guys sniffle and things. So if you have a question, go ahead and unmute yourself. But I've temporarily muted all of you. Okay, so conduction works the same way with electricity. If you physically touch something that is charged up, the charge can transfer to you. So the girl here who's holding onto the Van de Graaff generator, because she's physically touching it, then the electricity is conducted through her arm and up to her hair. So we call that charging by conduction. Okay. Now, another way things can work is charging by induction, which is what you see here. So what's happening here is we've got a ball. This is going to be a metal sphere, and it initially was not charged. Now, when I say not charged, that does not mean that it doesn't have any charges in it. What it means is it has equal amounts of positive charge and negative charge. Okay, so what happens is when we take a charged rod here, so we got a rod here that's negatively charged. If we bring it close to the ball, but we don't touch it, we just bring it close. Okay, what happens is the charges in the ball here, they will rearrange themselves, because remember what I said, like charges repel, opposite charges attract. Okay, so the plus charges that you see right here, they can feel the presence of all these negative charges, so they get pulled over to the left side, and all the negative charges, they get pushed off to the right side. So this ball has become charged by induction. Now, as soon as we take away the rod, those plus and minus charges will go back to mixed up to be the way they originally were, but it will temporarily be charged by induction. So if we want to permanently charge something by induction, you have to get creative here. Okay, so here is a page from your book, and you can see right here we've got two balls that are initially not charged. And so what we're doing is we're putting them so that they can touch each other, but nothing's going to happen because neither one has an excessive charge on it. And then we take this rod that has negative charge and we bring it close to one of them. And so what's going to happen is that because these two guys are touching each other, all of the plus charges from the guy on the right here, they can all get pulled over to the left, and all the minus charges, they can get pulled over to the right. So you get an excess of plus charges built up on the left and excess of negative charges on the right. And here's the important thing. While that rod is still in place, then separate the two balls, and then and only then take the ball out of the picture, or take the rod out of the picture. Okay, so then we started off with two uncharged objects, and by this clever technique here, we've ended up with two objects where one of them is positively charged and the other one's negatively charged, and that's called charging by induction. Okay, so can you guys give me some thumbs up or thumbs down to let me know if what we're doing so far makes sense? I'll wait here. Okay, so makes sense, smiley face, yes, jaw, okay, good. All right, okay, so now that we know that basic stuff, now let's go back to semiconductors and let's talk about semiconductors and how they work, because what I just talked about is the key to how they work. Okay, so remember how I said that a semiconductor can either be a conductor or an insulator depending on how you treat it. Well, the incredibly useful thing about semiconductors is that if you do it right, you can make it so that it will temporarily be a conductor. And then as soon as you stop doing whatever it is what you were doing, it immediately switches back to being an insulator again. So you can switch between being an insulator and a conductor depending on how you treat it. And that's an astoundingly, amazingly useful feature. That's the key to how our digital age works. Let's see, I see a question from Hunter here. Okay, good. You know, Hunter, I like the way you think, because that's exactly. So Hunter is saying, what use would that have? So I presume Hunter was looking at this when he asked that question. I asked the exact same question. When I read the book, I saw this and I looked at it and I said, okay, but so what? What use is that? Well, here is the use. It's in semiconductors is where they're used. Okay, so let's see how a computer memory chip is made. Now, some of you know that there are different types of computer memories. There's DRAMs there's flash memory, there's EEPROMs, there's all sorts of things. So I'm only going to talk about one type of memory. It's called a DRAM, that stands for Dynamic Random Access Memory. Okay, here's the thing. Okay, and so this is where we're going to store a bunch of ones and zeros that if we store enough of them and we're clever in how we do it, we can store pictures and music and all sorts of wonderful things there. So I'm going to start off down at the bottom of the screen here with a piece of silicon. So imagine that we've got a piece of silicon and we've sliced it. So let's see. Okay, so if this is the silicon, I'm not looking down on it from above, but I'm even with it, so I'm looking at it on side view of the silicon. And silicon is a semiconductor. So what that means is, if it's absolutely pure, if you have been very careful when you're making the silicon so there's no impurities whatsoever, it is a very good insulator. But if you introduce any impurities, and when I say any, I'm talking like part per million. If you just get a couple parts per million of impurities in there, it becomes a conductor, and a pretty good conductor at that. Okay, so I've got this slab of silicon. What I'm going to do is I want to drill a hole. Okay. I meant to bring this over. So one thing that you would think that I do, you take a drill here and drill a hole. Now, obviously, that's not the way that it's really done, because we're talking super microscopic, and you can't drill things super microscopically. But there are ways where you can put little tiny holes in there, and we're going to coat that hole with a conductive metal. Okay, and so this is where we want to store the charges, and we're going to call this a capacitor. In fact, let me get this back out here again. So I'm going to give this a name of a capacitor. So a capacitor is just something that can store charge, and capacitors usually only store charges temporarily. If you want the capacitor to store charge permanently, you have to get clever in how you do it. It can be done. Okay, so we've drilled a hole in our silicon, we've coated it with metal, and so think of it like a little coffee cup, and what we want to do is we want to put a bunch of charge in there, and we want that charge to stay there when we want it to, but we also want to be able to remove that charge when we want to. Okay, so let's go to the next step. Okay, so what we're doing right here is we are putting some impurities in certain locations. Now, again, I don't want to go into details of how that's done in the real world because it's really pretty complex. But if you think about, just imagine that you've got a gun and you can shoot atom by atom and you can aim very precisely. So what we're going to do is we're going to aim this gun, and we're going to purposely introduce impurities in this region right here and also in this region right here. So what happens to a semiconductor when it has impurities in it? Can somebody just type it in just so that I know that you guys are awake?
Mr. Hendricks, I have a question.
Okay.
What is an impurity?
Okay, an impurity is anything that is not silicon. So like an atom of something else. The atoms that they use in semiconductors are either boron or phosphorus. Those are the ones that work the best, but basically anything that is not silicon. Okay. All right. Okay, so Kiker is saying they become conductive, so very good. I'm glad to see that. Okay, so we have very carefully shot a bunch of non-silicon atoms into here and here. So this region here is conductive, this region here is conductive, but in between, it's still pure silicon. So in between them, it's still a good insulator. All right, so let's go to the next step. So I'm going to take this battery that you see here. Now, right now, the switch is open, so the electricity can't get in there. But I'm going to hook it up like this, okay? And now when I close the switch, the charges flow from the battery into here, and anything that flows into this region right here, it can move around wherever it wants, but it cannot leave that region because it's surrounded by an insulator. Our goal is to somehow get those charged particles over, or those charges, get them into the conductor here. That's our goal. But as you can see right now, we have not achieved our goal because we've got this non-conductive insulating region here. And so the charges did not get into the capacitor. All right, so what we want to do is we want to design a way where we can get the charges in there, and then once they're in there, we want to trap them in there. Okay, so here's how we're going to do that. We're going to take the silicon that we've got, and we're going to put a tiny piece of glass in this region in between the two conducting regions. And by the way, let's give that a name. So I'm going to call that the channel region. Okay. Okay, so the region in here, this is the channel. This is where, if I do things right, the electricity can either flow or not flow depending on how I've got things set. So we call that the channel. And so this is the insulating glass that we put down there. So next thing we do is on top of that glass, we put a conductor. It could be metal. In the early days when semiconductors were first made, it was in fact metal. Nowadays, they use other types of materials, but I want to keep things really simple. And so I'm going to call it metal, even though it doesn't have to be. Okay, so above our channel now, we have this thing that, let's give it a name. I'm going to call it the gate. Okay, so that's the gate up there. And down here was the channel. Okay, and a gate does exactly what you would think a gate would do. It's something where you can open it and you can close it. Okay, all right, so let's go to the next level here. Okay, so just a reminder of what we've got. We've got the metal, and this metal here could be the same metal as we have in our capacitor, or it could be different, doesn't have to be. Okay, all right, now, last thing we're going to do is we're going to cover everything with a blanket of insulating glass. So everything is now buried under glass so that if we could somehow get charges in there, the blanket will keep them in there. Okay, so Theo wants to know if we're ignoring ground for now. The answer is yes. Okay, any other questions? Okay. All right, so we put a blanket of insulating glass, which is also called oxide, by the way. Silicon dioxide is basically glass. Okay, so now, just a quick summary of what we got. So we got down here, we got the pure silicon. Over here in these blue regions, we have the doped silicon or the insulating, or I'm sorry, the doped silicon or the silicon with the impurities. And we got glass here, conductor here. Okay, so we're ready to go. So now let's start doing something. Okay, so what you see here is I've drilled two little holes here through the blanket, and I've attached wires. So I can go through this wire to get into the region on the left side, and I can go through the blanket to get into the gate. Now, right now, my switches are open, so nothing is happening. But let's close one of those switches. So I've closed the switch. So now the charges can get into this region right here, but they still can't get to the capacitor. But wait, okay. What happens if I were to put a charge on the upper region? Remember what we called that upper region there? Okay, we called that the gate. Okay, so this upper region here that we called the gate, okay, if I close the switch to my battery, so I've put charge on the gate now, here's where things get really interesting. Can that charge make it through to get into the substrate below? Well, the answer to that is no, because we've got this thin layer of insulating glass down there. So it can't get through there. But remember charging by induction? Remember when we talked about charging by induction? That's what's going to happen here. Okay, because the silicon below, it's neutrally charged. That doesn't mean that it's uncharged. It just means it has equal numbers of plus charges and minus charges. So when we put charge on the gate up there, we get a whole bunch of plus charges on the gate. So we get charging by induction, which means that in the substrate below, the negative charges, they get pulled up close to the gate, and the plus charges, they all get pulled away. And now we have an excess of electrons in the silicon right below the gate. That excess of electrons is an impurity. And what happens when you have an impurity? The silicon becomes conductive. So what we've done is we've now made that region underneath the gate so it is now conductive. So if we now close the lower switch, now you can see the electricity can now flow through the channel into the capacitor, and we can charge up the capacitor. Okay. Now, the last thing we need to do is we want that charge to stay there. Because we want to store a picture of our girlfriend or boyfriend or our favorite music or whatever. We want to store that in our smartphone. So we put a bunch of ones in there and also put zeros. You can do the same thing. And we need it to stay there. So how do we get it to stay there? Well, I'm sure you guys can guess. What we're going to do is we're going to undo the switch up here. So all those plus charges that were on the gate here, those plus charges, they all dissipate. What happens in the channel region underneath the gate? All those electrons that were there, they go back to where they came from because they're no longer being attracted by the plus charges up in the gate. So the electrons all go back to where they're coming from. And so what we have just done is we have now closed the gate. So all of these plus charges that we put over here in the capacitor, they cannot escape. They've got a blanket of oxide on top of them. They're surrounded by silicon, which is an insulator. They can't go anywhere. So we have just stored a digital 1. And I'm sure you can see that using the same technique, you can either store a 0 or 1 depending on how you do it. And then if you get clever with your zeros and ones, you can store photographs and music and whatever you want. Okay, so that is how semiconductor memory works. And the key to this particular type of memory is charging by induction. Okay, so give me thumbs up or okay, what's the purpose of the channel region? Well, the purpose of the channel region is that's where the electricity flows. So down here, let me go ahead and label it. Okay, so channel. Okay. So the channel right there, that's the path through which the electricity flows. So the channel is only available to let stuff flow if the gate is turned on. If the gate is turned off, then your channel is no longer a channel. Does that answer your question, Maddie? And how about the rest of you? Can you give me thumbs up or thumbs down on does this make sense? Okay, so I'm seeing lots of yeses.
I'm good.
Okay, clear as water. Okay, that's good. Okay, all right, so you see now charging by induction actually is an incredibly useful thing. And semiconductors are incredibly useful because you can make it be a conductor temporarily and then you can make it not be a conductor anymore. Okay, that's an incredibly useful thing. Okay, now in your homework tonight, they are not going to ask questions about this. But I think it's important that you need it, that you do this. So when you look on Canvas, you're going to see an extra credit assignment in there. And the extra credit assignment is basically just to see if you can restate what I have just told you. So there's a form on there. If you just go in and there's a bunch of pictures kind of similar to what you're seeing on the screen right now. So if you just go in and complete the picture and answer the questions, I'll give you credit, and it's extra credit. So go ahead and do that. Okay, so Joseph is saying, wait, so do we call it a semiconductor or do we call it a partial conductor? Well, we're going to call it a semiconductor because that's what it is. It can be a conductor sometimes, it can be an insulator sometimes, and it can change its state. That's what makes a semiconductor, is the fact that it can change between the two. Okay, now let's get back to the kinds of things that you are going to be seeing in the regular homework tonight, things from the book. Okay, so what you see right now is a page from the book where they're talking about the forces So you remember how we said that like charges repel, opposite charges attract. Okay, so we need to calculate how strong the force is. All right, so there is a scientist whose name was Coulomb, and he did a lot of work with this. And so he is the one that gets the credit for it, and the equation is named after him. So Charles Coulomb was his name. Okay, so what he did was he did a bunch of experiments. And so the first thing he did was just, he tried increasing the charge. So let's say I've got a charge here that has a certain number of electrons in it, and a charge here that has a certain number of electrons, okay? And he found that if you double the amount of charge, it doubles the force. And it doesn't matter if I double the charge on this guy, it doubles the force. If I double the charge on this guy, it also doubles the force, okay? So in other words, as you can see here, the force is proportional to the charge on each object, okay, which makes sense. But, you know, it might have been different. It might have been proportional to the charge squared. You know, we've had several instances throughout the year where that's been the case. But here we found that it's proportional to the charge. Oh, and by the way, we should also talk, when we're using Coulomb's law, the Q that you see here that represents the charge, Q does not, repeat, not represent the number of electrons. Because if we did that, we would have numbers that were so huge that it'd just be ridiculously absurd. So what we do is we create a unit. Kind of think, you know, a gallon of water. If we want to know how much water we have in a bucket, we don't count how many molecules there are. What we do is we've defined some quantity that we call it a gallon. And a gallon is just some certain number of molecules. Turns out to be a really large number. Okay, well, we do the same thing with electricity. If we were to count the number of electrons, the numbers would be so big they'd be absurd. So what we do is we have what's kind of the equivalent of a gallon of electrons, except we don't call it a gallon, we call it a coulomb. So you're going to see that a lot from now on. We're going to talk about how much charge we have. We're going to say how many coulombs do we have. So a coulomb is a certain number of electrons, and it turns out to be a really, really big number. Okay, so we know that the force, the number of newtons of repulsive force or attractive force is proportional to how much charge is on this guy, and it's also proportional to how much charge is on this guy. But there's more to it. We also need to think about the distance between them. So if two guys are really close together, the force is really strong. As the distance as they get further apart, the amount of force goes down. And so Charles Coulomb, when he was doing his experiments, he tried where he doubled the distance. And what he found was when he doubled the distance, the force did not go to 1/2 of what it was. It went to 1/4 of what it was. And when he tripled the distance, the force did not drop down to 1/3 of what it was. It dropped down to 1/9. So you guys all know what that means. That means that the force is proportional or it's inversely proportional to the distance squared. Okay, so we get this equation right here that you see on the screen, but I'm sure you guys know what's going to come next with. So Theo, hold your question there. I'll come back to your question in a minute, Theo. So I'm sure you guys know what's coming next, right? What am I going to say next?
It means a constant.
Okay, yeah. What I'm going to say next is I don't like proportional signs. I like equal signs. So if I want to change it to an equal sign, what do I have to do? Somebody type it in. If I want to change that proportional sign to an equal sign, what do I have to do? I have to add in a constant, or I have to throw in a constant. Yeah. Okay. So here we go. All right. So this is the equation that you're going to be using a lot in your homework tonight. And this is called Coulomb's equation. Okay. And so how do you find out what the value of that constant is? Well, experimentally. All right. So you take a certain known amount of charge on the one object, known amount of charge on the other. You know the distance, you measure how many newtons of force it is, and that way you can calculate the K value. And you can see right here, so experimentally, they've determined that the K value is about 9 × 10⁹. Now, it's not exactly that. if you guys look in the back of your books, okay, so your book here, if you look in the very, very back page, okay, there's a bunch of really useful information there. And one of the things you'll find there is the exact value, or you'll find out the value of K with more sig figs than just 2. You'll find out the actual value is about 8.99. Actually, let's see. Looks like it's, oh, need my glasses. Where's my glasses? Anyway, you can look it up. Oh, here they are. Okay. Yeah, I hate needing glasses. Okay, so the actual value is 8.98775 and a bunch more times 10 to the 9th. So when you're doing the homework tonight, you're going to have to do a bunch of equations where you have to use this equation right here. So if you only need 2 sig figs, then just call it 9.0. But if you need more than 2 sig figs, then make sure you use the actual value. Okay, so the first couple of homework assignments, or a couple of problems they give you, they're going to tell you, I've got a charge here. Let's say it has, 3 coulombs, and I've got another charge here that's, let's say 7 coulombs, and they're separated by a distance of 12 meters. And then they're going to ask you to calculate the force. Do you guys agree that that's easy? Give me yays or nays. Do you agree that's really, really easy?
Yes, it is.
Okay. Now, you know what I'm going to say after that, right? I'm going to say easy, right? Too easy, right? Well, we don't want it to be too easy. We don't want you guys to be bored. Okay. So how could we make this more interesting? How about
Equation?
say that again?
Another equation?
Well,
Do it in
how about
space.
how about if instead of having a one-dimensional problem, how about we have a two-dimensional problem? Okay. Let's do a problem like this. Okay. So what you see here is we have we have 3 charges. Okay. And so what's going to happen is we're going to have to solve this using, we're going to break them up into their pieces. And so what we're going to do is first, we're just going to look at charge A and charge B. We're going to pretend like charge C is not even there. We're just going to say, okay, if I've got charge A and charge B, and we know how much it is. In fact, if you go over here, this is a problem right straight from the book. Okay, so you can see they tell you how much charge is on sphere A. They're saying that it's 6 microcoulombs. They tell you how much is on sphere B, and they also tell you that there's a third sphere, which is C. Okay, so how do you do it? Well, first thing you do is you ignore sphere C completely. Just pretend like the only things that are in the object or in the world are A and B. And when you do that, you will get a force. Okay, and so this force that you see right here, this is the force that object B is exerting on A. Just that guy right there. But then you come back and then you say, but that's not the only object. There's also object C. And the colors here represent plus and minus. So you can see A and B are different colors. So that means that they are attracting each other. So that's why the force is on this force that you see here. This is the force on object A. So that's why it's pulling it off to the right. But A and C, you can see they're the same color. That means they're the same charge. So that means they repel each other. So if you look up on here, you can see the force of object C on object A is an upward force. So we've got 2 forces. One's going horizontal, one's going vertical. Boy, if only we knew about vectors. Boy, wouldn't it be handy if we knew how to add vectors? Do we know how to add vectors? Give me Ian. Ian, please don't ever do that again. Okay. I'm serious. Don't ever make comments like that on here again. Okay. All right. So direction and magnitude, we can do that. All right. So you guys, you can handle 2-dimensional problems. Okay. So I'm not going to go through this example. I don't think it's necessary for me to do it. If you look in the book, I think they've done a really good job of going through and telling you how to solve this problem. So I think we're good. Let me tell you what the homework assignment is. Okay, so you have to do problems 1 through, what did I say here? 1 through 13 is what I want. So 1 through 8, you can see here that those problems don't have the yellow background. So you're not going to be able to see the answers in the back of the book. But also you don't have to do as much computation. These are more conceptual things. These are just testing to see if you understand the general concept of how electricity works. Now problems 9 through 13, that's where you have to do some calculations. I think it's straightforward. Do you guys agree? Give me yays or nays as to whether or not you guys agree that this is pretty straightforward. Okay, I'm seeing lots of yays. Okay. All right. Well, I think we're good, Dan. Let's see. So when you look on Canvas, you'll see a regular homework assignment, which is the one that I just described. You'll see an extra credit problem, which is this one that you see on the screen right now. This extra credit problem is called the Physics of Computer Chips Part 1. The reason I say Part 1 is because there are different types of computer memory. There's RAM, there's ROM, there's flash memory, there's EEPROM, there's all sorts of different kinds. So this only talks about the kind of computer memory that's called the DRAM, which is a good way to temporarily store memory. Later in the year, we're going to talk about a different type of computer memory. It's called flash memory. Flash memory works with a different, through a different process. But in order to understand how flash memory works, we first have to understand how quantum mechanics works. You guys have, I've been threatening you all year long with quantum mechanics and warning you that quantum mechanics is coming and it's weird. Well, it is coming and it is weird, but it's also incredibly useful. The memory in your phones is flash memory, and flash memory wouldn't work on the technique that we've just talked about here. Flash memory requires quantum mechanics, and I promise you we will talk about it. Probably in about a month, if all goes well with the coronavirus, we're going to learn about quantum mechanics, and then we're going to learn about flash memory and how flash memory works. Okay, so I think we're done. Let's look over here. So Anna has a question. Anna says that even though I said the quizzes were easy, are they still able to be retaken? Yes. The answer to that is yes.
Mr. Hendricks, I also have a question about the quizzes.
Okay.
So because they're after the class period has happened, are we still going to do a coin flip every time, or will they all be recorded?
They're all going to be recorded. No coin flips anymore. Okay. Any other questions about anything? About the homework, about the extra credit, about how class is going to work during the coronavirus shutdown?
I have another question.
Okay.
Are labs going to happen at all?
That's a tough one. I have given that a lot of thought. I've tried to figure out, are there any ways that you could use materials that you have at your home and do a meaningful lab? I have not yet figured out a way to do that. If any of you have ideas, I would love to hear them. In fact, how about this? You guys are always looking for extra credit, right? If you can think of a good lab that we could do, that students could do from their homes using materials that everybody would likely have in their homes, if you can email me a suggestion, and if I like it and use it, I will give you extra credit. Ellie is asking if you still have late passes. The answer to that is yes. I will still allow late passes. 2 passes, and it's a new term now, so everybody starts out with 2. And if you had any left over from last term, sorry, they don't carry over. Okay, Joey is asking, does static electricity change the dynamic as soon as it starts moving? Yes, Joey, it does. You got it exactly right. Any other questions? Okay, no questions from him. Okay. All right, so I'm going to assume there are no more questions. So I'm going to stop the recording right now. And okay, and then I'll post it on, so the recording will be posted on the same Canvas page where the quiz is. So you got the two of them right side by side. So if I ask a question during the quiz and you say, well, I don't remember the answer to that, but I remember he talked about it. Well, right up above the quiz questions will be the recording of this session. So they'll be on the same page. So I'm going to stop the recording now, and then I'll stop the class.